Welcome to our lesson on exponential functions. Today, we'll explore these powerful mathematical tools that model growth and decay in our world. We'll cover everything from their definition to practical applications, with clear examples along the way. Let's start with the definition. An exponential function has the form f of x equals a times b to the power of x, where is the initial value. The value when x equals 0, b is the base, a positive constant not equal to 1, and x is the independent variable or exponent. Now, let's interpret what these parameters mean for the behavior of the function. If b is greater than 1, the function models exponential growth. Think of a population that doubles every generation or money growing with compound interest. If b is between 0 and 1, the function models exponential decay. This could represent radioactive decay, or the depreciation of a car's value. The parameter simply scales the graph vertically and must be non-zero. Now, let's explore the basic properties of exponential functions. First, the domain and range. The domain of an exponential function includes all real numbers, since we can raise b to any power. For the range, if it is positive, then the function values are always positive, giving us a range from 0 to positive infinity. If it is negative, the range is from negative infinity to 0. The y-intercept occurs when x equals 0. Since b to the power of 0 is 1, the y-intercept is simply a. An important feature is the horizontal asymptote. As x approaches negative infinity, b to the power of x approaches 0. So the function approaches the x-axis. This means y equals 0 is a horizontal asymptote. Let's learn how to sketch an exponential function. We'll sketch the function f of x equals 2 times 3 to the power of x. Step 1. Plot the point at x equals 0. Since the y-intercept is a, which is 2 in our case, we plot the point 0, 2. Step 2. Calculate some additional points. For example, when x equals 1, f of 1 equals 2 times 3 to the power of 1, which is 6. When x equals negative 1, f of negative 1 equals 2 times 3 to the power of negative 1, which is 2 times 1/3, giving us 2/3. Step 3. Draw a smooth curve through these points that approaches the x-axis as x approaches negative infinity, and grows rapidly as x approaches positive infinity. Now, let's learn how to solve exponential equations. To solve an equation like a times b to the power of x equals c, we follow these steps. Step 1. Isolate b to the power of x by dividing both sides by a. Step 2. Apply logarithm to both sides. We can use natural log or log base 10. Step 3. Use the property of logarithms to bring down the exponent, and then solve for x. Let's work through some examples to practice solving exponential equations. Example 1. Solve 5 times 2 to the power of x equals 40. First, we isolate 2 to the power of x by dividing both sides by 5. This gives us 2 to the power of x equals 8. Now, we can recognize that 8 equals 2 cubed, so x must equal 3. Example 2. Solve 3 times 0.5 to the power of x equals 1.5. Isolating the exponential term, we get 0.5 to the power of x equals 0.5. Since 0.5 equals 0.5 to the power of 1, we conclude that x equals 1. Example 3. Solve 7 times 3 to the power of x equals 20. Isolating the exponential term, we get 3 to the power of x equals 20 divided by 7. Taking the natural logarithm of both sides, x times ln of 3 equals ln of 20 over 7. Solving for x equals ln of 20 over 7 divided by ln of 3, which is approximately 1.771. Exponential functions have numerous real-world applications. Let's explore some of these applications. First, population growth can be modeled using the formula p of t equals p0 times e to the power of r times t, where p0 is the initial population, r is the growth rate, and t is time. Second, radioactive decay follows the model a of t equals a0 times e to the power of negative k times t, where a0 is the initial amount and k is the decay constant. Third, compound interest uses the formula a of t equals p times 1 plus r divided by n, all raised to the power of n times t, where p is the principal, r is the interest rate, n is the number of compounding periods per year, and t is time in years. Finally, let's discuss the difference between continuous and discrete exponents. For discrete modeling, we use a general base b, as in the form b to the power of x. For continuous processes, we often use the special base e, which is approximately 2.71828. This special number e is particularly useful for natural growth and decay processes and appears in the form e to the power of k times x. Let's summarize what we've learned about exponential functions. First, we identified the components of the exponential function f of x equals a times b to the power of x. Second, we learned how to sketch exponential functions by plotting key points and recognizing the horizontal asymptote at y equals 0. Third, we practiced solving exponential equations by isolating the exponential term and taking logarithms. And finally, we explored real-world applications of exponential functions in population growth, radioactive decay, and compound interest. Understanding exponential functions is crucial as they model many natural and financial processes in our world. Thanks for watching.